Going for BCC structure, body centered cubic lattice indicates number of atoms in the corners, corner atoms plus body center. Corner atoms plus body center. Now this is a BCC structure. We have corners 8. Now one body center. Now this is a BCC structure. So taking out now to find out the coordination numbers and the neighboring atoms and nearest distances. So this is a reference atom. Now this is an atom separated with the distance A. This is an atom separated with the distance root 2A. Now we have one more body center separated with the distance. Total body diagonal is root 3A. Then half this total is root 3A. This is the body center atom. Half of this value root 3A by 2. So these are the 3 atoms separated with the different distances. Say this is atom 1. Say this is atom 2. This is atom 1 I am marking. This is atom 2 I am marking. This is atom 3 I am marking. This is 1, 2, 3. Then for atom 1, root 3A by 2. For atom 2, A. For atom 3, root 2A. Since it is separated with the minimum distance, now this is known as nearest atom and next one, and this is next one, and so on you can go. Now I need number of neighboring atoms. Again I am taking this is a point for this reference to this. Now this is a reference. So how many have same type of atoms? This is 1, this is 2, this is 3. So here contribution is 1 by 4. So 8, 3, 1 by 4. This is nothing but 6. So here neighboring atom 6, nothing but coordination. Similarly, sorry, this is for next atom. I need for next atom. Coordination number 6. Now, for root 3A by 2, I am going. Second one. Now, this is the reference atom. Now, I am taking body center. Only one atom in the body center. So, 8 into 1 into 1 equal to 8. So, here 8. Now, this is known as coordination number. Similarly, for this atom, root 2A, this is an atom, number of neighbors requires. Number of neighbors. This is a reference atom. Now, this is the one body diagonal. Phase diagonal. This is the second phase diagonal. We have one more here. Again, phase diagonal. This is the phase diagonal. This is the phase diagonal. Then one more here, phase diagonal. So total 3 atoms. So 8 into 3. Contribution is half. Nothing but 12. So again 8, 6, 12. So 8, 6, 12 is nothing but neighboring atoms in BCC. The first one is known as coordination. And this is how you can find out coordination numbers, number of neighboring atoms in SCC and FCC and BCC. To find out these coordination numbers and neighboring atoms, I was considered isolated only 8 unit cells. Okay, keep it in mind. Right. Discuss about coordination numbers and neighboring atoms. One topic. Now, next topic is voids. So, void is nothing but a space between atoms. Empty space between atoms is known as void. For example, these are the two atoms and one more atom I am drawing. Three atoms which are arranged in one layer. The space between is known as the space. The space between these three atoms is known as void, nothing but hole. Now this is the center of an atom, center of an atom, center of an atom. I can make a triangle. Now this is known as triangle void. Similarly, four atoms. This is a 1, this is 2, this is 3. One layer. On the top I can keep one more. Now the empty space between all these four atoms is known as void. That void is known as tetrahedral void. That void is known as tetrahedral void. You can draw. Now this is tetrahedral. Now this is one atom. This is second atom. This is third atom. This is the fourth atom. All these atoms are in contact with each other, and hence this is known as tetrahedral void. This is known as tetrahedral void. Similarly, this is one. So four atoms in contact. Now this is a square planar. On the top of this, one more atom. On the right side, you have one more atom. So total 6 atoms forming one hole. That hole is known as octahedral hole. So simply octahedral hole can draw is octahedral on the top one here and the bottom one here. Now this is octahedral hole, or nothing but voids. So these are the some type of voids: tetrahedral voids, then octahedral voids, then you have triangular void. This triangular void, this is tetrahedral void, and this is octahedral void. Now, tetrahedral voids and octahedral voids, particularly location of these two voids in FCC structures required. Location of tetrahedral voids and octahedral voids in FCC structure. So FCC structure is nothing but, as you know, this is FCC structure. FCC structure would like to find out tetrahedral voids and octahedral voids. So I am considering now this is the FCC structure. Now in FCC structure, I am not marking all the atoms, only I am marking a particular atoms. Phase center, this is one phase center, second phase center, third phase center, fourth phase center, and fifth one, and sixth one. So 6 phases we have. So I am joining all these. Now this is square planar. All these atoms are touching each other. Then on the top one, on the bottom one. So making all these atoms one whole. Now this whole is known as octahedral void. This whole is nothing but octahedral void. That octahedral is exactly at the body center. Because at the body center, the hole is formed. That hole is known as octahedral void. So only one hole, the contribution also one. If anything is present in the middle, it belongs to only that one itself. So 1 into 1 equal to 1. So one octahedral void at body center, F6 is at body center. Similarly, now this is a one corner atom, this is the second corner atom. Next, this is the third corner atom. Now this one attached to the other unit cell. So there we have one more phase. So making this is one. So I can separately I can draw to show other octahedral voids. So again I am drawing FCC. Now this is FCC structure. At other places also you can find. At other places also you can find. Now this is a corner atom. This is a corner atom. This is a phase atom. Now this unit cell is sharing with the other unit cell. There also you have one phase atom. So I can join all these four. Then this is the square planar. Then here one more phase center atom, and here also one more phase center atom. So all these things making one whole. Total 6 atoms now, making one whole. That whole is, this is the edge. This is edge now. That whole is formed on the center of the edge. Now this is known as edge center. So in FCC structure, octahedral voids are located at body center, only one, and edge centers, on edge centers. So total number, how many octahedral voids if existing at edge centers. So now I can find out how many edges you have in the cube. There are 12 edges in the cube. If atom is present, this is edge. If here one more, this is octahedral. This is edge. One more. This is edge. This is edge. This is edge. This is edge. And here also this is edge. And here also this is edge. Here also this is edge. And here this is edge. And here this is edge. This is edge. So total 1. This is at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total 12 edges if present in the edge center, contribution is 1 by 4. Its contribution is 1 by 4, and hence there are 12 edge centers. Contribution to each one is 1 by 4. So 1 by 4 into this is nothing but 3. So effectively, to one unit cell of FCC containing 3 octahedral voids, the position is edge center. Position is edge center. Position is edge center. So total voids, octahedral voids equal to 3 are edge center, 1 is body center. So total how many you have? 4. So 3 body center, 1, 3 edge centers, and 1 is body center. So total octahedral voids in FCC structure 4. Similarly, you have tetrahedral voids also. So tetrahedral voids, to find out tetrahedral voids. Tetrahedral voids in FCC structure. Now this is FCC structure. This is FCC structure. So this is a corner atom. Now to this corner atom, here is one more, the phase center, and here phase center, and here phase center, back center. So I can join all these 3 and make this 4. Now there is a formation of void or hole. Now this is known as tetrahedral. Now tetrahedral void is nothing but form one corner atom, left side face, top face, and back side face. So this is a total one cube. I can cut this cube into 8 other cubes. The cube form is known as mini cube. Now I can mark in the mini cube. This is a mini cube. So this is one item. This is one item. This is one atom, and here is one atom. So making all four, there is a formation of pole. That pole is exactly in the center of mini cube. So total making one corner. This is a corner atom. One corner atom forming one tetrahedral void. So total how many corners you have? 8 corners. This is also corner atom. It can form one more tetrahedral. It can form one more tetrahedral. Like this, we have 8 corners. If that void is a tetrahedral void is formed only center of the cube and no more related to the other sharing, involved in the sharing, and hence 8 into 1 equal to 8. So these are nothing but tetrahedral voids. The tetrahedral voids are how many? 8 entirely belongs to only that unit cell. No sharing, no contribution involved. Right? Octahedral voids are 4. Tetrahedral voids are 8. So I can say octahedral voids equal to 2 into tetrahedral voids equal to 2 times octahedral voids. Similarly, in the FCC arrangement, so you know the lattice points, phase and corners. Phase and corners are occupied with anions. So total how many phases? 6 phases. Contribution is half. Corners 8. Contribution is 1 by 8. So total 3 plus 1 equal to 4 ions. 4 cations, 4 anions here. Now cations are in octahedral poles. In FCC structure, cations in goes to octahedral voids because their size exactly fit into the octahedral. So total how many octahedral voids? We have 4 octahedral voids, and hence these are number of anions I can say. So number of cations equal to 4. So these are known as ion pairs. So in FCC, effective atoms equal to 4. I can say octahedral voids is nothing but 7. So now from the effective number of atoms, you can find out octahedral. Twice the number of effective numbers is raised to tetrahedral. So location of all these 8 tetrahedral voids in the FCC, we have 4 body diagrams. In FCC, we have 4 body diagrams. Now, this is FCC structure. This is a corner atom. For this corner, 1 tetrahedral void. Again, this is also corner. Then another tetrahedral. For this corner, I can write 1 tetrahedral void. And here also 1 tetrahedral void. Again, for these 2 corners, 1 tetrahedral void, 1 tetrahedral void. Again, for these 2 corner atoms, I can draw. This is 1 tetrahedral void. This is 1 tetrahedral void. Again, these two corner atoms, these two corner atoms, I can draw. So these are the position of tetrahedral voids in FCC structure. You have 4 body diagonals. 4 body diagonals in FCC. How many body diagonals? 4 body diagonals in FCC. So each body diagonal having 2 tetrahedral whites. So 4 into 2 equal to 8 tetrahedral whites. Can draw now. This is nothing but this is the body diagonal. Now in this body diagonal, this is the corner diagonal, this is the corner diagonal. So each body diagonal, how many you have? 2 tetrahedral whites. So I can draw. Imagine this is a body diagonal. This is one corner. This is the second corner. Last corner. Now you have tetrahedral whites. This is tetrahedral white. This is tetrahedral white. One end and second end. Now this is a total body diagonal. Body diagonal having distance root 3a. Total distance. Total distance is root 3. Now corner to tetrahedral white. Corner to tetrahedral white is 1/4 of this value. So root 3a by 4 is distance between corner atom and tetrahedral white. Similarly, here also you have root 3a by 4 distance between tetrahedral and other corner atom. Now these two are separated with the distance half of the value. So distance between two tetrahedral whites is root 3a by 2 and one corner and tetrahedral white is root 3a. So total 4 body diagonals, location is this. Now in JEE Advanced, you can get the question like, so I am making, so these are 8 tetrahedral whites. They may ask the question like this. So question I am marking now. So you have 4 tetrahedral whites and here also 4 tetrahedral whites. Joining all together, you can make one cube. So I am making now. Now this is a one small cube. Now this is the one small cube. So with the help of tetrahedral whites, I was drawn one cube inside unit cell. Would like to find out number of tetrahedral whites, number of octahedral whites in the cube form. In the cube form, just I was given total 8 tetrahedral whites. Making use of 8 tetrahedral whites, I made one cube, small cube, inside the big cube or inside the unit cell. In this, I need to find how many number of tetrahedral whites effectively in the newly formed cube. Similarly, number of octahedral whites in the newly formed cube. Question clear now? Now, simple to answer this question. As you know, this is a big unit cell. Now, in the big unit cell, at the body center, which void is existing? At the body center, you can find one void. That void is known as octahedral void. Since this is belongs to only that unit cell, and hence contribution is 1. So in the small unit cell, one octahedral, that is nothing but fully occupied octahedral, one full octahedral void. Similarly, now number of tetrahedral voids. Have to check number of tetrahedral voids. To check number of tetrahedral voids, just consider this as a cube. Now in the cube, the tetrahedral is formed at corner. Tetrahedral void is formed at corner. If it is formed at corner, contribution to other thing is 1/8. Contribution to each one is 1/8. So like this, how many you have? 1 by 8, 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 1 by 8. So total 1 by 8 into 8 is nothing but 1. So this mini cube inside a small cube containing one full tetrahedral void and one full octahedral void. So you may get question like this. A new cube is formed. They may ask question like this. New cube has been formed by joining all tetrahedral voids in a unit cell, in FCC unit cell. Find which is the correct statement. Option 1. Newly formed cube has one full tetrahedral void. Second one, only. Second one full octahedral void only. Next, third one full octahedral void and one full tetrahedral void. And fourth one, no tetrahedral void and 1 by 8 octahedral voids. 1 by 8 octahedral voids. So they may ask the question like this. So you should think in a broad manner to find out such kind of questions. So one is full tetrahedral, one is tetrahedral, one full octahedral. So as a whole, in FCC structure, location of voids was explained. Location of voids. So location of voids is nothing but we have tetrahedral voids, we have octahedral voids. So octahedral voids are 4, 3 head centers, 1 body center. Number of effective atoms in FCC 4. So nothing but number of effective atoms always equal to octahedral voids. Similarly, tetrahedral voids. Inside the cube, you have 8 tetrahedral voids, double the number of octahedral voids. Now distance between two tetrahedral voids root 3a by 2. Corner and tetrahedral void is root 3a by 4. So total 4 body diagonals. So place of that tetrahedral voids 2 on each body diagonals. So this is about the concept of identifying voids in FCC structure. Say for example, these are the 4 atoms arranged tetrahedrally. Now this is known as tetrahedral void. Suppose I am keeping an atom here, B. Its coordination number is nothing but 4 because it is surrounded by 4 other atoms. Now I need its coordination number. Suppose this is an atom A and this is B. Now its coordination number is 4. Now this unit cell, this is an atom common to 8 other unit cells. 1, 2, 3, 4, 5, 6, 7 and 1 is this. So coordination number for this is 8. So this atom coordination for this atom coordination number 8, for this atom coordination number 4. Say for example, they will do AB. This is the short formula AB. These are tetrahedral. Given in the question, it was given. Then ask you to find coordination number of A. Then ask you to find coordination number of A. Now to find out coordination number, very simple. First you check the stoichiometric ratio. 1:2. This is the stoichiometric ratio. Then to find out the coordination number, simply go for reverse. 2:1. That 2:1 is coordination number. To find the coordination number of atoms. Just a simple logic. Tetrahedral coordination number, you know. What is the coordination number for tetrahedral? 4. For atom A, I need in the ratio 2:1. So 4 times 2, 8. So coordination number is 8. Just now was explained. So from the formula, you can find out stoichiometric. From the stoichiometric ratio, you can find out the coordination number. So this is how the concept of tetrahedral voids, octahedral voids in FCC structure. Then, based on these two topics, so far what I was explained, coordination numbers, neighboring atoms, in simple cube, FCC body center. Then based on tetrahedral and octahedral voids, now we can go over doing some numericals.